13.8 billion years ago, everything that exists burst into being from a region smaller than the period at the end of this sentence. But here is what will blow your mind. Before that moment, there was no space, no time, no matter, no energy, no laws of physics. There was literally nothing. Yet somehow, nothing became everything. Scientists have discovered that quantum mechanics makes the impossible possible, that invisible membranes might collide in dimensions we cannot see, and that our entire cosmos could be the output of a black hole in another reality. If you enjoy learning about the universe's deepest mysteries, hit that like button. Prepare yourselves. We begin. Picture absolute darkness stretching forever with no sound, no light, no atoms, no space for anything to exist in. Most people imagine that before the Big Bang, there was simply nothing at all, a complete void, empty blackness waiting for something to fill it. But this picture is completely wrong, and understanding why changes everything about how we think about the birth of our universe. The problem starts with the word before. When we say before the Big Bang, we are assuming that time already existed, ticking away like a cosmic clock, waiting for the universe to suddenly appear. But according to our best physics, time itself was created in the Big Bang. There was no before, because before and after are concepts that only make sense when time exists. Think of it like asking what is north of the North Pole. The question sounds reasonable until you realize that north loses all meaning at the North Pole itself. Similarly, before the Big Bang is a meaningless phrase because time starts with the Big Bang. But even if we ignore this time problem, the idea of absolute nothingness runs into an even bigger obstacle. Quantum mechanics, the most successful theory in the history of science, tells us that true nothingness is impossible. At the smallest scales, space itself bubbles with activity. Virtual particles pop into existence and vanish again in fractions of a second. Energy fluctuates wildly. The quantum vacuum is not empty space waiting to be filled, but rather the most active, energetic state possible. Here is where it gets strange. The Heisenberg uncertainty principle says that you cannot know both the position and momentum of a particle with perfect accuracy, but it also says something even more radical about energy and time. For extremely brief moments, the universe can borrow enormous amounts of energy from nowhere, as long as it pays the energy back quickly enough. The shorter the time, the more energy can be borrowed. Scientists have calculated that in a region the size of a proton, quantum fluctuations create and destroy the equivalent mass energy of about 100 particles every second. Scale this up to the entire observable universe, and the numbers become mind-bending. We are talking about energy levels that dwarf every star in the galaxy combined, all hiding in what we call empty space. This quantum foam is not some theoretical curiosity. We can measure its effects in laboratories. The Casimir effect shows that metal plates placed incredibly close together in a vacuum will attract each other because of the pressure from virtual particles. Quantum fluctuations are as real as the ground beneath your feet. So the question is not how something came from nothing. The question is how the violent, churning quantum vacuum that physicists call nothing managed to create the smooth, expanding space-time we call home. But that transformation required a trigger unlike anything we have ever seen. Energy cannot be created or destroyed. So how did 13 billion tons of matter suddenly appear? This question kept physicists awake at night for decades after the Big Bang theory was proposed. Every high school student learns that energy is conserved. You cannot get something from nothing. It is the most fundamental law in all of science. Yet here we are, living in a universe that seems to have violated this law on the grandest scale imaginable. The breakthrough came when scientists realized they had been thinking about energy conservation all wrong. The law works perfectly within our universe, but the creation of the universe itself might follow different rules. It turns out that the total energy of everything that exists might actually be zero. Here is how this works. Take every star, every planet, every atom in the observable universe, and add up all their mass energy using Einstein's famous equation. The number is staggering, about 10 to the 54th power joules. That is a 1 followed by 54 zeros. Written out, this number would stretch across several pages. But there is another type of energy we need to account for: gravitational potential energy. When objects are pulled together by gravity, they have negative energy compared to when they are infinitely far apart. Think of rolling a ball down a hill. At the bottom, the ball has less gravitational energy than at the top. In fact, if you set the energy at infinite distance to 0, then the energy at any finite distance is negative. Now comes the remarkable part. When physicists calculate the total gravitational potential energy of all matter in the universe, they get a negative number whose absolute value nearly equals the positive mass energy of all matter. The universe's energy books appear to balance almost perfectly. This means the Big Bang did not create energy out of nothing. Instead, it separated the positive energy we see as matter from an equal amount of negative gravitational energy. Like tearing apart a piece of paper creates two edges where there was once a seamless surface, the Big Bang split zero total energy into positive and negative parts. But this raises an even deeper question. Even if the energy books balance, what provided the initial push to start this cosmic separation? Conservation of energy allows the universe to exist, but it does not explain why anything started happening in the first place. The answer requires us to think about the nature of nothing itself. In quantum mechanics, nothing is not stable. Empty space is constantly fluctuating, with virtual particles appearing and disappearing. Most of these fluctuations cancel out immediately, but occasionally, for reasons we are still trying to understand, a fluctuation becomes real and permanent. Scientists call this a vacuum fluctuation. It is like the surface of a perfectly calm pond, suddenly producing a wave from nowhere. Except in this case, the wave became our entire universe. However, there was one tiny problem with this beautiful theory that would soon reshape everything we thought we knew about cosmic origins. At this very moment, invisible particles are popping into existence right in front of your face and vanishing before you can detect them. This is not science fiction. This is quantum mechanics, and it happens everywhere, all the time, including in the space between your eyes and this screen. These phantom particles, called virtual particles, are born from the quantum vacuum and live for such brief moments that they normally cannot affect the world we see. But occasionally, they do something extraordinary. Werner Heisenberg discovered that there is a fundamental limit to how precisely we can know certain properties of particles. His uncertainty principle is usually described in terms of position and momentum, but it has an even more dramatic consequence for energy and time. For incredibly short periods, the universe can create particles out of pure vacuum as long as they disappear quickly enough. The more massive the particle, the more energy is needed to create it, which means it must vanish even faster. An electron-positron pair can exist for about 10 to the minus 21st power seconds. A proton-antiproton pair gets only 10 to the minus 24th power seconds. These timeframes are so short that light cannot travel even the width of a proton during their entire existence. Picture the quantum vacuum like a bustling marketplace where vendors set up shop, sell their goods, and vanish before anyone notices they were there. Except instead of selling vegetables, they are lending energy to create matter, and instead of money, they pay with time. The more they borrow, the faster they must disappear. Scientists have measured these virtual particles indirectly through their effects on real matter. When electrons orbit atomic nuclei, their energy levels shift slightly because of interactions with virtual particles. This Lamb shift, measured to extraordinary precision, proves that the quantum foam is real. But here is where things get truly strange. Under very special circumstances, virtual particles can become real and permanent. If something provides enough energy at exactly the right moment, a virtual particle pair can avoid annihilation and join the permanent matter of our universe. The most dramatic example occurs near black holes. The intense gravitational field can rip virtual particle pairs apart before they can recombine. One particle falls into the black hole, while the other escapes as real, detectable radiation. Stephen Hawking showed that this process causes black holes to slowly evaporate by radiating energy. Now, imagine this happening not with a few particles near a black hole, but with every single atom in the observable universe. Imagine a quantum fluctuation so massive that it creates not just a particle pair, but an entire cosmos. The energy required would be beyond comprehension, except for one crucial detail we discovered in the previous chapter. If the total energy of the universe is zero, then creating it requires no net energy at all. A quantum fluctuation could, in principle, create equal amounts of positive matter energy and negative gravitational potential energy. The universe could be the ultimate free lunch, paid for by the uncertainty principle itself. But quantum fluctuations are random and unpredictable. What could have made one particular fluctuation grow into our ordered, structured cosmos, while countless others simply vanished into the void? The answer lies in a field that once dominated our universe, but has since nearly disappeared. Even in the emptiest regions of space, where not a single atom exists for millions of miles, there is still something there. Scientists call it vacuum energy, and it is one of the most mysterious forces in the universe. Unlike the matter and radiation we can see, vacuum energy is a property of space itself. Every cubic inch of empty space contains a small but measurable amount of energy, and this energy has a very unusual property. It creates a repulsive gravitational effect. This sounds impossible. We think of gravity as always attractive, always pulling things together. But Einstein's equations allow for gravity to become repulsive under very special circumstances. When energy density remains constant even as space expands, the resulting pressure becomes negative, and negative pressure creates repulsive gravity. Think of a stretched rubber band. The more you stretch it, the more it wants to contract. But vacuum energy behaves like an anti-rubber band. The more space expands, the more vacuum energy appears to fill the new space. And the more this energy pushes space to expand even faster. In our current universe, vacuum energy is incredibly weak. It creates what we call dark energy, responsible for the accelerating expansion we observe today. But calculations suggest that in the earliest moments after the Big Bang, vacuum energy was much, much stronger. During those first tiny fractions of a second, vacuum energy drove a period of exponential expansion called cosmic inflation. Space expanded faster than the speed of light, growing by a factor of at least 10 to the 26th power in less than 10 to the minus 32nd power seconds. To put this in perspective, imagine a grain of sand suddenly becoming larger than a basketball, all in the time it takes light to cross the width of a proton. This inflationary expansion solved several major problems with the standard Big Bang model. It explained why the universe appears flat and uniform on large scales, why we do not see magnetic monopoles or other exotic particles, and how regions of space that are now billions of light years apart could have once been close enough to reach the same temperature. But inflation created a new mystery. What triggered this sudden burst of vacuum energy, and why did it stop? The best current theory involves a quantum field called the inflaton. Like all quantum fields, the inflaton fluctuates randomly. Most of the time, these fluctuations are small and temporary. But occasionally, a fluctuation pushes the field into a special state where vacuum energy becomes enormous. Picture a ball rolling around on a hilly landscape. Most of the time, it rolls into valleys and comes to rest. But if it happens to roll up onto a very flat plateau, it might coast for a long time before finding a way down. The inflaton field works similarly, except instead of a ball on a landscape, we have a quantum field exploring different energy states. When the inflaton field found itself on its special plateau, the universe inflated exponentially. When it finally rolled off the plateau, The stored vacuum energy converted into the hot, dense soup of particles that became everything we see today. This conversion process, called reheating, marks the end of inflation and the beginning of the more familiar hot Big Bang. But it also raises a profound question about the nature of quantum fluctuations themselves. The most perfect vacuum chamber ever created still bubbles with invisible activity that never stops. Scientists have built chambers where they remove every atom, every molecule, every particle they can detect. They cool these chambers to temperatures colder than outer space and shield them from every known form of radiation. Yet, even in these most perfect vacuums humanity can create, something is always happening. Quantum mechanics tells us that this activity is fundamental to the nature of reality itself. The universe operates on a principle of fundamental uncertainty that makes perfect stillness impossible. This uncertainty is not due to imperfect measurements or incomplete knowledge. It is built into the fabric of existence. The Heisenberg uncertainty principle states that certain pairs of properties cannot be measured with perfect precision simultaneously. The more accurately you know a particle's position, the less you can know about its momentum, and vice versa. But this principle extends beyond individual particles to the vacuum itself. Energy and time form one such uncertain pair. For very brief periods, the uncertainty in energy can become enormous. The quantum vacuum can borrow vast amounts of energy from nowhere, create virtual particles with that energy, and then pay back the debt by annihilating those particles before the universe notices. Picture reality like a cosmic bank with an unusual policy. You can take out any loan you want, as long as you pay it back before the bank's accounting system updates. The larger the loan, the faster you must repay it. Take out a small loan, and you have a relatively long time to pay it back. Take out a massive loan, and you must repay it almost instantly. Virtual particles are these cosmic loans made manifest. An electron and its antimatter twin, a positron, can borrow enough energy to pop into existence, orbit each other briefly, and then collide and annihilate, returning the borrowed energy to the vacuum. This entire process takes only about 10 to the minus 21st power seconds. We know these virtual particles exist because they have measurable effects. They alter the magnetic properties of electrons in atoms. They create forces between metal plates in vacuum chambers. They cause hydrogen atoms to emit light at slightly different frequencies than simple calculations predict. Most remarkably, virtual particles carry real momentum. When light passes through a strong magnetic field, virtual electron-positron pairs can briefly form, interact with the photons, and change the light's polarization. The virtual becomes real enough to alter what we observe. This quantum foam of virtual particles means that the concept of empty space is meaningless. There is no such thing as true nothingness, only different levels of somethingness. The vacuum is not the absence of everything, but rather the lowest energy state that quantum mechanics allows. But if the vacuum always has some energy, and if quantum fluctuations can temporarily create much higher energy states, then occasionally a fluctuation might not disappear. Under the right circumstances, a quantum fluctuation could become permanent and grow into something much larger. The question is, what makes a fluctuation permanent rather than temporary? The answer involves the most powerful repulsive force the universe has ever known. But this force did not act alone. It needed help from something that most people have never heard of, yet which may have determined the fate of everything that exists. Every atom in your body contains enough energy to power a city for months, yet the universe might have exactly zero total energy. This paradox goes to the heart of one of the most elegant solutions to the question of cosmic origins. If the universe has zero total energy, then creating it required no energy input at all. The Big Bang did not violate conservation of energy because it never created any net energy in the first place. The positive side of the cosmic energy ledger is easy to see. Every particle has mass, and Einstein showed us that mass is a form of energy. The protons and neutrons in atomic nuclei, the electrons orbiting around them, the photons streaming from stars, the neutrinos passing through the Earth every second, all represent positive energy. Add up all the matter and radiation in the observable universe, and you get a number so large it defies comprehension. The total mass energy equivalent is about 10 to the 53rd power kilograms. That is a 1 followed by 53 zeros worth of kilograms. Written out, this number would cover several pages. But there is another form of energy that is much harder to see: gravitational potential energy. When objects are bound together by gravity, they have less energy than when they are infinitely far apart. Think of a book sitting on a shelf. It has gravitational potential energy relative to the floor. Drop the book, and that potential energy converts to kinetic energy as the book falls. In the same way, every particle in the universe has negative gravitational potential energy relative to a state where all particles are infinitely separated. The stronger the gravitational field, the more negative this energy becomes. And since gravity in our universe is always attractive, gravitational potential energy is always negative. When physicists calculate the total gravitational potential energy of all matter in the observable universe, they find that its magnitude nearly equals the positive mass energy of all matter. The cosmic books balance to within the accuracy of our measurements. This means the universe could have emerged from a quantum fluctuation without violating energy conservation, like a quantum loan that never needs to be repaid because the total debt is zero. The universe represents a split of nothing into equal positive and negative parts. But this raises a new question. Even if creating a zero-energy universe requires no net energy input, what determined the specific form our universe took? Why did we get 3 dimensions of space and 1 of time? Why do particles have the masses they do? Why are the fundamental forces as strong as they are? Some scientists propose that all possible universes with zero net energy actually exist somewhere. We observe this particular combination of properties because we happen to exist in a universe where these properties allow complex structures like stars, planets, and living beings to form. Other scientists suggest that the universe started in a completely random state and evolved toward its current form through physical processes we do not yet understand. The early universe might have been a chaotic soup where space and time themselves were constantly changing, eventually settling into the stable configuration we observe today. But perhaps the most intriguing possibility is that our universe is not unique at all. Perhaps the quantum vacuum constantly creates new universes, each with different properties, in a process that has been going on forever. This possibility leads us to one of the most profound ideas in modern cosmology: that our Big Bang was not the beginning of everything, but simply one event in an infinite cascade of cosmic creation. In 1973, Edward Tryon shocked the physics community by suggesting that our entire universe is nothing more than a quantum hiccup that forgot to disappear. Tryon was attending a seminar at Columbia University when the speaker mentioned the problem of why the universe exists at all. Without thinking, Tryon blurted out, "Maybe the universe is a vacuum fluctuation." The room fell silent. Some colleagues laughed. Others looked embarrassed for him, but Tryon realized he might have stumbled onto something profound. The idea seemed absurd at first. Vacuum fluctuations create virtual particles that exist for incredibly brief moments before disappearing. An electron-positron pair might exist for about 10 to the minus 21st power seconds. How could a fluctuation lasting such an impossibly short time create a universe that has existed for almost 14 billion years? Tryon worked out the mathematics and found something remarkable. The larger the fluctuation, the longer it can potentially last before disappearing. A fluctuation that creates just 2 particles must vanish almost instantly. But a fluctuation that creates an entire universe worth of matter and energy could persist for tens of billions of years and still satisfy the uncertainty principle. The key insight was the total energy calculation we explored earlier. If the universe has exactly zero net energy, then quantum mechanics places no time limit on how long it can exist. A zero-energy fluctuation can last forever without violating any physical laws. Think of it like a cosmic accounting error that never gets corrected because the books still balance. The universe borrowed infinite positive energy and infinite negative energy simultaneously, leaving a net debt of zero. As long as the total remains zero, the cosmic bank never demands repayment. But Trion's proposal faced a serious challenge. Even if a universe-sized fluctuation could last long enough, why would it evolve into the ordered, structured cosmos we observe? Random fluctuations should create random universes, chaotic soup with no galaxies, no stars, no planets. The answer came with the discovery of cosmic inflation in the 1980s. Alan Guth showed that if the early universe contained a special type of energy field, it would expand exponentially, smoothing out any initial chaos and creating the uniform conditions needed for structure formation. Inflation solved the randomness problem, but it created a new one. What caused inflation to start and stop at just the right times? The answer required physicists to think more carefully about the nature of quantum fields themselves. Modern theories propose that the quantum vacuum contains many different energy fields, each with its own landscape of possible values. Most of the time, these fields sit quietly in their lowest energy states, but occasionally, quantum fluctuations kick a field into a higher energy state, where it drives exponential expansion. Trion's original idea has evolved into something even more radical. Instead of one lucky fluctuation creating our universe, the quantum vacuum might constantly create new universes through inflation. Each time a field fluctuates into its high energy state, a new region of space undergoes exponential expansion, effectively budding off as a separate universe. This process, called eternal inflation, means our Big Bang was not the beginning of everything, but simply one bubble in an infinite foam of expanding universes. Each bubble has its own physics, its own history, its own version of reality. If this picture is correct, then asking what caused our Big Bang is like asking what caused today's weather while ignoring the global climate system. Our universe is part of something much larger and more complex than we ever imagined. But even eternal inflation leaves the deepest question unanswered. Where did the quantum fields come from in the first place? In less time than it takes light to cross the width of a proton, our universe grew from smaller than an atom to larger than a grapefruit. This period, called cosmic inflation, represents the most extreme expansion in the history of the universe. Space itself stretched faster than the speed of light, increasing in size by at least 26 orders of magnitude in about 10 to the minus 32 power seconds. Nothing has moved that fast or changed that dramatically ever since. The discovery of inflation solved major puzzles about the Big Bang. Without inflation, the universe should be curved rather than flat, lumpy rather than smooth, and filled with exotic particles that we never observe. Inflation explained all these features by showing that exponential expansion could stretch any initial curvature flat, smooth out any initial lumpiness, and dilute exotic particles to undetectable levels. But inflation created its own mystery. What provided the enormous energy needed to drive this expansion? The answer involves a quantum field that scientists call the inflaton. Though no one knows exactly what this field really island. Picture the inflaton as an invisible energy that fills all of space, like water filling a fish tank. But unlike water, this energy has the bizarre property that it creates more of itself as space expands. The more space grows, the more inflaton energy appears, and the more this energy pushes space to grow even faster. Think of it like a magical bank account where depositing $1 automatically deposits another dollar, which deposits another dollar, which deposits another, forever. Except instead of dollars, we are talking about the energy that curves space-time and drives cosmic expansion. For inflation to work, the inflaton field must start in a very special state. Scientists describe this using the metaphor of a ball rolling on a hilly landscape. Most of the time, balls roll into valleys and come to rest. But if a ball finds itself on a very flat plateau, it can roll for a long time while barely losing height. The inflattened field was like a ball that found itself on such a plateau. While it remained there, its energy density stayed nearly constant even as space expanded exponentially. This constant energy density is what drove the accelerated expansion we call inflation. Eventually, the inflaton field rolled off its plateau and converted its stored energy into the hot soup of particles that filled the early universe. This reheating process marked the end of inflation and the beginning of the more familiar Big Bang evolution that created atoms, stars, and galaxies. But what put the inflaton on its plateau in the first place? This question brings us back to quantum fluctuations. Just as virtual particles can briefly borrow energy from the vacuum, quantum fields can briefly fluctuate to higher or lower values than their equilibrium states. Most field fluctuations quickly decay back to equilibrium, like waves on a pond settling to calmness. But occasionally, a fluctuation might push a field like the inflaton into its special plateau state. Once there, the field would drive inflation, creating a region of exponentially expanding space that could become a universe. This picture suggests that inflation is not a one-time event, but an ongoing process. Somewhere in the broader structure of reality, quantum fluctuations are constantly triggering new episodes of inflation, creating new universes that bud off from the multiverse, like soap bubbles forming in a cosmic bath. Our universe would then be just one such bubble, born from a quantum fluctuation in a much larger and stranger reality. At this very moment, countless new universes might be bursting into existence in dimensions we cannot see or reach. The theory of eternal inflation paints a picture of reality so vast that our observable universe, containing hundreds of billions of galaxies, becomes just a tiny bubble in an infinite cosmic foam. This is not science fiction, but a serious consequence of our best theories about how inflation works. Here is how eternal inflation operates. Imagine the quantum vacuum as a vast ocean filled with energy fields that constantly fluctuate up and down. Most fluctuations are small and temporary, like gentle waves that rise and fall without consequence. But occasionally, a fluctuation pushes a field into a special high-energy state that drives exponential expansion. When this happens, a region of space inflates exponentially, growing from microscopic to macroscopic size in an infinitesimal fraction of a second. But here is the crucial point. Inflation does not happen everywhere at once. Different regions enter and exit inflation at different times, creating a patchwork of expanding bubbles separated by regions that are still inflating. Think of it like popcorn popping in a giant cosmic pot. Some kernels pop early, others pop late, and new kernels are always heating up and getting ready to pop. Except instead of kernels, we have regions of space, and instead of popping into fluffy corn, they pop into entire universes. Each universe bubble has its own physics. The fundamental constants that determine particle masses, force strengths, and even the number of spatial dimensions can vary from bubble to bubble. Most bubbles probably cannot support complex structures like atoms, molecules, or life. They might be filled with nothing but radiation, or dominated by forces so strong that matter cannot form stable configurations. Our bubble happens to have physics that allows stars to shine for billions of years, planets to form around them, and complex chemistry to create living beings. We observe this particular set of physical laws not because they are special or predetermined, but because we could not exist in bubbles with different physics. Scientists call this the anthropic principle. It does not require any designer or purpose, just the simple observation that conscious beings can only find themselves in universes where consciousness is possible. But eternal inflation raises profound questions about the nature of reality itself. If new universes are constantly being created, and if most of them have physics completely different from ours, then what we call the laws of nature might be just local bylaws in our particular cosmic neighborhood. Moreover, if inflation is truly eternal, then every possible universe that can exist does exist somewhere in the multiverse. There would be universes where history unfolded differently, where you made different choices, where the laws of physics vary in every conceivable way. This picture is so radical that some physicists reject it entirely. They argue that untestable theories about unobservable universes are not science, but philosophy. Others embrace the multiverse as the natural conclusion of our best physical theories. The debate continues, but eternal inflation makes specific predictions about our own universe that we can test. The pattern of temperature variations in the cosmic microwave background radiation should bear the signature of quantum fluctuations that occurred during inflation. Future observations might prove or disprove whether our universe really did emerge from this process. But even if eternal inflation is correct, it pushes the ultimate questions about existence one level higher. Instead of asking why our universe exists, we must ask why the multiverse exists. Instead of explaining the origin of space and time, we must explain the origin of the quantum fields that create space and time. The search for answers leads us into even stranger territory, where the very concept of dimensions becomes far more complex than anyone imagined. Somewhere in the invisible foundations of reality lurks a force so powerful it can stretch space faster than light itself travels. Scientists call this mysterious entity the inflaton field, but despite decades of searching, no one has ever detected it directly. We know it must exist because nothing else can explain the extraordinary uniformity and flatness of our universe. Yet, the inflaton remains as elusive as a ghost, leaving only indirect traces of its cosmic influence. Think of the inflaton as an invisible energy that fills every point in space, like an ocean that exists in dimensions we cannot perceive. Unlike ordinary matter and energy, this field has the bizarre property of creating more of itself as space expands. The more universe there is, the more inflaton energy appears to fill it, and the more this energy drives further expansion. This sounds like it violates conservation of energy, but it does not. The positive energy stored in the inflaton field is exactly balanced by negative gravitational potential energy created by the field's effect on space-time curvature. The total energy remains zero, just split between positive and negative forms. For inflation to work correctly, the inflaton must have very specific properties. Its energy density must remain nearly constant as space expands exponentially. It must convert smoothly into ordinary matter and radiation when inflation ends. And it must create exactly the right pattern of quantum fluctuations to seed the formation of galaxies and larger structures. Scientists describe these requirements using the metaphor of a ball rolling down a hill. The inflaton's energy is like the height of the ball, and different energy values correspond to different positions on the landscape. For inflation to occur, the ball must find itself on a very flat plateau, where it can roll slowly while barely losing height. Most theoretical landscapes do not have such flat plateaus. This is called the flatness problem of inflation. Why would a quantum field naturally settle into such an unusual configuration? It is like asking why a ball would roll uphill onto a perfectly level table when most balls simply roll down into valleys. One possibility is that our universe is just incredibly lucky. Among all the quantum fluctuations that have ever occurred, one happened to push the inflaton onto its special plateau, triggering the inflation that created our cosmic home. But this explanation requires extraordinary fine-tuning that makes many physicists uncomfortable. Another possibility is that inflation happens much more easily than we think. Perhaps there are many different types of inflaton fields, or perhaps the landscape has more flat plateaus than simple models suggest. If inflation is easy to trigger, then it might happen constantly throughout the multiverse, creating an endless supply of new universes. Recent observations from satellites studying the cosmic microwave background have ruled out the simplest inflaton models. but have not eliminated inflation itself. The data suggests that whatever drove inflation had properties more complex than early theories predicted. Some physicists propose that the inflaton is not a single field, but a combination of multiple fields working together. Others suggest that inflation was driven by quantum effects in extra dimensions of space that we cannot directly observe. The mystery deepens when we realize that the inflaton field must have appeared from somewhere. Even if quantum fluctuations triggered inflation, those fluctuations required pre-existing quantum fields to fluctuate. We have not solved the origin problem, but merely pushed it back one level. The search for the inflaton's true identity leads us into the realm of string theory and extra dimensions, where the familiar three dimensions of space expand into a complex multidimensional architecture that defies visualization. The largest structures in the universe began as quantum fluctuations smaller than a single proton that got stretched to cosmic proportions. This transformation represents one of the most remarkable amplification processes in all of physics. Quantum fluctuations that were originally smaller than any atom eventually became the seeds from which galaxies, galaxy clusters, and the vast cosmic web of dark matter grew. Understanding how this happened reveals the deep connection between the quantum world and the cosmic architecture we observe today. During inflation, the inflaton field was not perfectly smooth, but exhibited tiny random fluctuations due to quantum uncertainty. These fluctuations were minuscule, varying from place to place by only about 1 part in 100,000. Yet, they contained the blueprint for everything we see in the night sky. Picture a balloon covered with microscopic wrinkles that are invisible to the naked eye. Now imagine inflating that balloon until it becomes the size of Earth. Those tiny wrinkles would grow into mountains and valleys, easily visible from space. Cosmic inflation did something similar to quantum fluctuations in the inflaton field. As space expanded exponentially, quantum fluctuations that started smaller than the Planck length grew to astronomical scales. Regions where the inflaton field was slightly denser became the locations where matter would later clump together to form the first stars and galaxies. Regions where the field was slightly less dense became the cosmic voids that separate galaxy clusters today. The amplification factor is almost impossible to comprehend. A fluctuation that began smaller than 10 to the minus 35 power meters grew to sizes of millions of light years across. That is an increase of more than 60 orders of magnitude, like inflating a grain of sand until it becomes larger than the entire solar system. But quantum fluctuations are random, so how did they create the organized structures we observe? The answer lies in the physics of gravity and the behavior of dark matter in the early universe. After inflation ended and the universe filled with ordinary matter and radiation, gravity began pulling matter toward the slightly denser regions created by inflaton fluctuations. These regions acted like cosmic magnets, attracting more and more matter over millions of years. Dark matter, which interacts only through gravity, clumped together first because it was not slowed down by electromagnetic forces. Dark matter halos formed around the densest regions, creating gravitational wells that later captured ordinary matter to form the first stars and galaxies. Computer simulations show that this process naturally creates the web-like structure we observe today, with galaxies connected by filaments of dark matter separated by vast empty voids. The pattern matches observations with remarkable accuracy, providing strong evidence that cosmic inflation really occurred. The cosmic microwave background radiation preserves a snapshot of these fluctuations as they existed 380,000 years after the Big Bang. Satellites like WMAP and Planck have mapped these temperature variations across the entire sky, revealing the quantum fingerprints that became galaxies. Different inflation models predict different patterns in these fluctuations. By comparing observations with theoretical predictions, scientists can test whether inflation really happened and learn about the physics of the inflaton field itself. The data confirms that the fluctuations have exactly the properties expected from quantum mechanics during inflation. They are nearly scale invariant, meaning they have similar strength at all size scales. They are also nearly Gaussian, meaning their distribution follows the random pattern expected from quantum uncertainty. But recent observations have revealed subtle deviations from the simplest predictions that hint at more complex physics during inflation. The three dimensions of space that define our everyday experience might be just a tiny fraction of reality's true architecture. String theory, our most ambitious attempt to unify all forces of nature, requires space to have at least 9 dimensions, with possibly even more dimensions beyond that. These extra dimensions are not science fiction speculation, but mathematical necessities for the theory to work correctly. Yet we never experience them directly because they are curled up so tightly that they remain invisible at human scales. Imagine looking at a garden hose from a great distance. It appears to be a one-dimensional line stretching across your yard. But move closer, and you discover that the hose actually has additional dimensions wrapped around that line. A tiny ant walking on the hose could move forward and backward along its length, but also around its circumference. The hose is really three-dimensional, but its cylindrical dimensions are so small compared to its length that they are invisible from far away. String theory suggests that our universe works similarly. We perceive 3 large dimensions of space, plus 1 of time, but additional spatial dimensions might be curled up at every point in space. These extra dimensions are compactified on scales smaller than atomic nuclei, making them impossible to detect with current technology. The shape and size of these extra dimensions determine the properties of particles and forces we observe in our three-dimensional world. Different configurations of extra dimensions produce different physics. Change the geometry of the hidden dimensions, and you change the masses of particles, the strengths of forces, even the number of particle types that can exist. This creates a vast landscape of possible universes, each corresponding to a different way of curling up the extra dimensions. The total number of possibilities might be as large as 10 to the 500th power, a number so huge that it dwarfs the number of atoms in the observable universe. Most of these possible universes would be completely unlike ours. They might have no stable atoms, no electromagnetic force, or gravity so strong that nothing larger than elementary particles could exist. Our universe represents just one tiny island of habitability in this enormous ocean of possibilities. But string theory raises a profound question. If reality has more dimensions than we can see, what exists in those hidden dimensions? Are there objects, forces, or even forms of life that operate in the full multidimensional space while remaining invisible to us? Some theories propose that our entire universe exists on a three-dimensional surface called a brane, embedded in higher dimensional space. We are like two-dimensional beings living on the surface of a balloon, unaware of the three-dimensional space that surrounds us. Other three-dimensional surfaces, carrying their own universes, might float nearby in the higher dimensional space. These parallel branes could be less than a millimeter away from us in extra dimensions, while remaining completely inaccessible because we cannot move through those dimensions. Gravity, however, might be different. While electromagnetic and nuclear forces are confined to our brane, gravity might spread out into the extra dimensions. This could explain why gravity is so much weaker than other forces. Most of its strength leaks away into dimensions we cannot access. The brane world picture opens up extraordinary possibilities for cosmic origins. If multiple branes exist in higher dimensional space, they might occasionally collide with each other. Such collisions would release enormous amounts of energy, potentially triggering events like the Big Bang. Instead of emerging from a quantum fluctuation in empty space, our universe might have been born from the collision of two membranes in a multidimensional reality, far stranger than anything we have imagined. Picture our entire universe as a soap bubble floating in a bathtub filled with countless other bubbles, each containing its own version of reality. This mind-bending possibility emerges from string theory's prediction that reality has more dimensions than the 3 of space and 1 of time that we experience. If extra dimensions exist, then objects called brains, short for membranes, could extend across multiple dimensions while confining certain types of matter and energy to their surfaces. Think of a brain like an incredibly thin sheet of paper floating in a 3-dimensional room. 2-dimensional creatures living on the paper's surface could move forward, backward, left, and right, but they could not move up or down into the room itself. They would be completely unaware of the 3rd dimension surrounding them. We might be like those 2-dimensional creatures, except living on a 3-dimensional brain floating in a space with many more dimensions. Everything we can touch, see, or detect with our most sensitive instruments might be confined to our brain, while vast regions of higher dimensional space remain completely inaccessible to us. The mathematics of string theory allows brains of different dimensions. There could be 1-dimensional strings, 2-dimensional membranes, 3-dimensional volumes like our universe, or even higher dimensional objects that have no analog in our experience. These brains can move through the higher dimensional space, stretch, vibrate, and interact with each other in complex ways. Most remarkably, brains can collide. When 2 3-dimensional brains crash into each other in higher dimensional space, they release enormous amounts of energy. This energy gets converted into matter and radiation confined to the brain's surfaces, potentially creating the hot, dense conditions we associate with the Big Bang. Scientists call this the ekpyrotic scenario, from the ancient Greek word for conflagration. In this picture, our Big Bang was not the beginning of time, but rather a collision between our brain and another brain that had been approaching through higher dimensional space for eons. The collision would explain many features of our universe that standard Big Bang theory struggles with. It would naturally produce a flat, uniform cosmos without requiring an initial period of inflation. It would create the right mixture of matter and radiation to match observations, and it would generate the pattern of fluctuations that later became galaxies and larger structures. But the ekpyrotic scenario raises its own puzzles. What determined the brain's initial positions and velocities? Why did they collide at exactly the right angle and speed to produce a universe like ours? And what prevented them from simply bouncing off each other or sticking together permanently? Some theories propose that brain collisions happen regularly, creating cycles of destruction and rebirth. Our universe might expand for trillions of years, eventually contract back to a point, and then experience another collision that triggers a new Big Bang. This cyclic model suggests that what we call the beginning of time is really just the latest episode in an eternal sequence of cosmic rebirths. Other theories suggest that our brain was created when a higher dimensional object split apart, like a soap bubble dividing into 2 smaller bubbles. The splitting process would release energy that becomes the matter and radiation filling our universe. These ideas remain highly speculative because we have no direct way to observe extra dimensions or detect other brains. The energies required to probe such small distances and high dimensions are far beyond anything we can achieve with current technology. But some effects of extra dimensions might be observable indirectly. If gravity spreads into extra dimensions while other forces remain confined to our brain, then gravity should become stronger at very short distances. Experiments are currently testing this prediction by measuring gravitational forces between objects separated by fractions of a millimeter. The possibility that our universe is just one brain among many, floating in higher dimensional space, represents one of the most radical revisions of reality that science has ever proposed. Imagine 2 sheets of reality, each containing billions of galaxies, racing toward each other through dimensions we cannot see at speeds that dwarf anything in our universe. The collision between such cosmic membranes would unleash energies that make the explosion of every star in our galaxy look like a firecracker. By comparison, when brains crash together in higher dimensional space, they do not simply bounce off each other like billiard balls. Instead, they stick together, merge, and convert their enormous kinetic energy into the fundamental particles and forces that fill a universe. Think of two sheets of wet paper slamming into each other. The impact creates ripples, tears, and regions where the sheets fuse together. But instead of paper and water, we are talking about the fabric of space-time itself, and instead of ripples, we get the birth of matter, energy, and the laws of physics. The mathematics of brane collisions predict that such an event would create exactly the conditions we observe in our universe. The collision would generate temperatures of trillions of degrees, hot enough to create every type of particle and antiparticle that exists. It would produce the right mixture of hydrogen and helium that we see in the oldest stars, and it would create tiny fluctuations in density that later grew into galaxies. Most remarkably, a brane collision naturally explains why our universe is so flat and uniform. In the standard Big Bang model, different regions of the universe that are now billions of light years apart could never have been in contact with each other, so there is no reason they should have the same temperature. But if our entire observable universe emerged from a collision between smooth brane surfaces, then uniformity becomes inevitable. The collision process unfolds in stages that mirror the known history of our universe. First, the approaching branes create gravitational waves that ripple through higher dimensional space. Then comes the moment of impact, when kinetic energy converts to thermal energy in a process far more violent than any explosion we can imagine. The newly created matter and radiation expand rapidly away from the collision zone. But this expansion is driven by the energy released in the collision rather than by mysterious inflation fields. Space stretches because it is filled with incredibly hot, dense matter moving at enormous speeds, not because of exotic quantum effects. As the collision debris cools and expands, protons and neutrons form from the quark soup, then atomic nuclei, then neutral atoms. Gravity amplifies tiny density variations left over from the collision, eventually pulling matter together to form the first stars and galaxies. But brane collisions raise profound questions about what determines their timing and violence. The branes must approach each other at exactly the right speed and angle to produce a universe like ours. Too fast, and the collision creates only radiation that quickly disperses. Too slow, and not enough energy gets released to heat the universe properly. Some theories propose that the branes are attracted to each other by forces operating in extra dimensions, like magnets pulling together through empty space. Others suggest that the collisions happen randomly, with most producing universes very different from ours. The most intriguing possibility is that brane collisions do not happen just once, but repeat in endless cycles. Our universe might be destined to expand for trillions of years, then contract back to a point, setting up the conditions for another collision that creates a new cosmos. But if branes can collide and create universes, could our universe itself exist inside something even larger and stranger? The moment of impact between two cosmic membranes would compress more energy into a single point than exists in 10 billion galaxies combined. This collision would not happen gradually, like two cars slowly bumping into each other. Instead, it would be instantaneous and absolute, with the entire surfaces of both branes making contact simultaneously across regions far larger than our observable universe. The energy released would be concentrated into a zone thinner than an atomic nucleus, but extending across countless light years. Picture two enormous sheets of rubber stretched tight and then slammed together with incredible force. The collision creates a shock wave that travels along both surfaces, heating them to unimaginable temperatures. But instead of rubber, these surfaces are the fundamental fabric of space-time itself, and instead of heat, the collision creates matter and energy. The first particles to emerge would be the most exotic and unstable varieties that exist only at the highest energies. Quarks and gluons would form in a soup so hot that atomic nuclei could not exist. The strong nuclear force that normally confines quarks inside protons and neutrons would be overwhelmed by the thermal chaos, leaving individual quarks to roam freely through space. As the collision debris expands and cools, phase transitions would occur that fundamentally change the nature of reality. First, quarks would bind together to form protons and neutrons. Then, as temperatures dropped further, electrons would join with atomic nuclei to create the first neutral atoms. Each transition would release energy and create the conditions for the next phase of cosmic evolution. The collision would also determine the fundamental constants of physics in the newly created universe. The masses of particles, the strengths of forces, and even the number of spatial dimensions would depend on the exact geometry of the colliding branes and the way they merge together. Different collision angles and speeds would produce universes with completely different physics. A head-on collision might create a universe dominated by radiation with no stable matter. A glancing blow might produce weak gravitational fields, unable to form stars and planets. Only collisions with very specific properties would generate universes capable of supporting complex structures. The brane collision model makes testable predictions about our universe that differ from standard inflation theories. Most importantly, it predicts that gravitational waves generated during the collision would have a specific pattern that should be detectable in the cosmic microwave background radiation. These primordial gravitational waves would carry information about the collision itself, like fossils preserving evidence of an ancient catastrophe. Future satellites, designed to measure polarization in the microwave background, might be able to detect these signals and tell us whether our universe really began with a brane collision. The model also predicts that our universe should have a slight preference for matter over antimatter, which matches observations. During the collision, subtle asymmetries in the brane surfaces could create slightly more particles than antiparticles, explaining why anything exists at all, instead of everything annihilating into pure energy. But perhaps the most profound implication of the brane collision model is that it makes our Big Bang into a local rather than universal event. While our region of space was being born from the collision, other regions of the branes might have been undergoing their own collisions, creating other universes with their own physics and histories. This raises the possibility that we live not just in a multiverse of quantum fluctuations and eternal inflation, but in a multiverse of colliding branes, where universe creation is an ongoing industrial process happening throughout higher dimensional space. Yet even this extraordinary picture might be too narrow, because some theories suggest our entire cosmic history could be playing out inside something even more bizarre. What we call the Big Bang might actually be the white hole explosion emerging from a black hole collapse in a higher dimensional reality. This mind-bending possibility suggests that every black hole in our universe could contain an entire cosmos like ours, complete with galaxies, stars, planets, and possibly life. Meanwhile, our universe itself might exist inside a black hole that formed when a massive star collapsed in a four-dimensional parent universe. The idea emerged from trying to understand what happens at the center of a black hole. General relativity predicts that matter falling into a black hole gets compressed into a singularity of infinite density, but physicists suspect this prediction breaks down when quantum effects become important. Instead of a singularity, something else might happen. One possibility is that the collapsing matter bounces back, creating what scientists call a white hole. While black holes pull everything in and never let anything escape, white holes push everything out and never let anything enter. A white hole would be like a Big Bang happening in reverse, spewing matter and energy into space. The mathematics are surprisingly elegant. When a massive star collapses into a black hole in four-dimensional space, the interior geometry could connect to a three-dimensional brane where the collapsed matter re-emerges as a white hole explosion. This explosion would create space, time, matter, and energy, exactly like our Big Bang. From our perspective inside the newly created universe, the white hole explosion would look identical to the standard Big Bang. We would see the cosmic microwave background radiation, observe the expansion of space, and measure the abundance of light elements, never suspecting that our entire cosmos is the interior of a black hole in a higher dimensional space. The black hole cosmology model solves several puzzles about our universe. It explains why the Big Bang happened when it did, rather than earlier or later. It occurred when the parent star collapsed. It explains why our universe has exactly the right density to be geometrically flat. This density is determined by the mass of the collapsed star. And it explains why we observe dark energy. The expansion of our universe reflects the ongoing growth of the black hole's interior. The model also makes testable predictions. If our universe is the interior of a four-dimensional black hole, then its expansion rate should change in specific ways as it ages. These changes might be detectable by measuring the distances to very remote galaxies with next-generation telescopes. More dramatically, the theory suggests that every black hole in our universe spawns a new cosmos. When a star collapses to form a black hole, it creates a three-dimensional universe that begins expanding from a Big Bang-like event. These baby universes are completely cut off from their parents, unable to send information back through the black hole's event horizon. This creates a cosmic evolutionary process, where universes that produce many black holes have many offspring, while universes that produce few black holes leave few descendants. Over time, the multiverse would become populated primarily by universes good at making black holes, which happen to be universes with physics similar to ours. The theory is difficult to test directly because we cannot observe anything inside a black hole from the outside, and we cannot see outside our universe from the inside. But indirect evidence might come from studying how black holes form and evolve, or from detecting subtle effects of the extra dimension on gravity and particle physics. If black hole cosmology is correct, then the question of what caused our Big Bang has a clear answer. It was caused by the gravitational collapse of a massive star in a parent universe. But this answer immediately raises new questions about the parent universe and its origins. The search for ultimate explanations leads us to consider whether universe creation might be a cyclical process with no true beginning. Our universe might be destined to collapse back into a singularity that immediately explodes outward as a new Big Bang, creating an eternal wheel of cosmic death and rebirth. This cyclical model of cosmology suggests that what we call the beginning of time is really just the latest episode in an infinite sequence of universal rebirths. Each cycle begins with a Big Bang, evolves through billions of years of expansion and structure formation, then reverses into a big crunch that sets up the conditions for the next cycle. The idea has ancient roots in Hindu and Buddhist cosmology, but modern physics gives it a sophisticated mathematical framework. Loop quantum gravity, one of the leading theories trying to merge general relativity with quantum mechanics, predicts that matter cannot be compressed to infinite density. Instead, quantum effects create a repulsive force that bounces the universe back from the brink of destruction. Picture the universe like a cosmic pendulum that swings from expansion to contraction and back again. At one extreme of the swing, space is stretched thin and cold, filled mostly with isolated black holes, slowly evaporating into nothingness. At the other extreme, everything is compressed into a hot, dense state that rebounds into a new Big Bang. The bounce happens when matter reaches the Planck density, about 10 to the 94th power kilograms per cubic meter. This is the point where quantum gravity effects become stronger than classical gravitational attraction. The collapsing matter hits this quantum wall and bounces back, triggering explosive expansion. Loop quantum cosmology calculations show that this bounce preserves information from the previous cycle. The new universe inherits memory of its predecessor in the form of quantum correlations that affect the pattern of cosmic microwave background radiation. Future observations might detect these signals from before our Big Bang. Each cycle could last trillions of years or more. Our universe is currently about 14 billion years old and still expanding. but observations show that expansion is accelerating due to dark energy. If this acceleration continues, the universe will expand forever, growing cold and empty as stars burn out and black holes evaporate. But dark energy might not be constant. Some theories predict that it will eventually reverse, causing space to contract rather than expand. The cosmic microwave background would blue shift to higher energies, galaxies would merge together, and eventually all matter would collapse back toward a big crunch. The bouncing universe model makes specific predictions about what happens during the collapse phase. As the universe contracts, black holes merge together into larger and larger holes. Eventually, all matter falls into a single cosmic black hole that then undergoes quantum gravitational collapse and rebounds. Different versions of the cyclic model propose different mechanisms for the bounce. Some invoke higher dimensional branes that collide repeatedly. Others rely on exotic matter fields that become repulsive at high densities. Still, others suggest that time itself reverses direction during the bounce, making the collapse phase actually be the expansion phase of the next cycle running backward. The cyclical picture has appealing features but also faces serious challenges. Each cycle must produce nearly identical initial conditions to explain why our universe looks so similar to what standard Big Bang theory predicts. The bounce mechanism must work perfectly every time, never failing to trigger the next expansion phase. Perhaps most problematically, the second law of thermodynamics says that entropy always increases over time. Each cycle should be more disordered than the previous one, eventually leading to a universe too chaotic to support structure formation. Solving this entropy problem requires either exotic physics or a mechanism to reset the universe's disorder level during each bounce. Despite these challenges, cyclical cosmology remains an active area of research because it offers something that other models cannot: a universe with no true beginning or end. But even cyclical models must explain how the endless sequence of bounces started in the first place. The most violent explosion in the history of our universe might have been the gentle end of a cosmos that existed for trillions of years before ours was born. This reversal of perspective transforms our Big Bang from a moment of creation into a moment of transformation. Instead of matter and energy appearing from nothing, they would be the compressed remains of galaxies, stars, and planets that once filled a previous universe. Our cosmic dawn would be their cosmic twilight. The transition from Big Crunch to Big Bang requires physics beyond anything we currently understand. As the previous universe collapsed, matter would be crushed to densities far exceeding anything inside atomic nuclei. At some point, the normal laws of physics would break down, replaced by quantum gravitational effects that reverse the collapse and trigger expansion. Think of the transition like a cosmic trampoline. The previous universe falls toward maximum compression, but just before reaching infinite density, quantum effects provide a bounce that sends matter flying back outward. The rebound becomes our Big Bang, launching the expansion that created everything we observe today. Loop quantum gravity provides the most detailed model of how this bounce might work. The theory suggests that space-time itself is made of tiny, discrete loops, rather than being perfectly smooth. When matter is compressed to the Planck scale, these quantum loops create a repulsive force that overcomes gravitational attraction. The calculations show that the bounce preserves many features of the previous universe while erasing others. Large-scale structures like galaxies and stars would be completely destroyed during the compression phase, but quantum information about the previous universe's geometry and matter distribution could survive the bounce and influence the initial conditions of the new expansion. This means our cosmic microwave background radiation might contain encoded information about the universe that existed before ours. The tiny temperature fluctuations that we observe could be quantum echoes of density patterns that existed trillions of years ago in a completely different cosmic era. Future experiments might be able to decode these signals and reconstruct aspects of the pre-Big Bang universe. Scientists are developing techniques to search for specific patterns in the microwave background, that would indicate a quantum bounce rather than inflation or other Big Bang mechanisms. The bouncing universe model raises profound questions about cosmic evolution. If universes cycle through endless sequences of expansion and contraction, do they evolve over time? Could each cycle be slightly different from the previous one, leading to a gradual change in the laws of physics or fundamental constants? Some theories suggest that information processing and computation could occur during the collapse phase, with the entire universe becoming a kind of cosmic computer that calculates the initial conditions for the next cycle. The previous universe might have literally computed our universe into existence. Other theories propose that consciousness itself could play a role in determining how the bounce occurs. If intelligent beings in the previous universe developed technology capable of influencing quantum gravitational effects, they might have been able to program the initial conditions of our universe. This raises the extraordinary possibility that our Big Bang was not a random event, but a deliberate act of creation by advanced beings who knew their universe was ending. They might have encoded information, knowledge, or even themselves into the quantum fluctuations that became our cosmic microwave background. The bouncing universe model also suggests that our universe will eventually face the same fate. Trillions of years from now, if dark energy reverses and space begins contracting, we might find ourselves in the same position as our cosmic predecessors. But perhaps consciousness and intelligence will play an even more direct role in universe creation than anyone has imagined. What if the Big Bang required not just quantum fluctuations and energy fields, but something even stranger, an observer to collapse the wave function of reality itself? This possibility emerges from one of the deepest mysteries in quantum mechanics, the measurement problem. Quantum systems exist in superposition states, where they have multiple properties simultaneously until someone observes them. The act of observation causes the wave function to collapse, forcing the system to choose one specific state. But who or what observed the Big Bang? If the entire universe began as a quantum fluctuation, then the fluctuation should have remained in superposition until something measured it. Without an observer, the Big Bang might never have become real, leaving existence trapped forever in a state of pure possibility. Some interpretations of quantum mechanics suggest that consciousness is what collapses wave functions. In this view, quantum systems only become definite when observed by conscious beings. Before consciousness evolved, the universe would have existed in a hazy superposition of all possible histories simultaneously. The implications are staggering. According to this interpretation, the universe only became real retroactively when the first conscious observers appeared billions of years after the Big Bang. Their observations reached backward through time, collapsing the cosmic wave function and determining which of the infinite possible Big Bangs actually occurred. Think of it like a cosmic detective story, where the crime only happens when someone discovers the evidence. Until conscious beings evolved and began observing the universe, there was no definite history, no specific initial conditions, no particular values for the fundamental constants of physics. This retroactive Genesis model suggests that consciousness is not just a byproduct of cosmic evolution, but an essential ingredient in the creation process. The universe needed to evolve conscious observers in order to become real in the first place. We are not just witnesses to cosmic history, but active participants in determining what that history was. The theory faces obvious philosophical challenges. How could consciousness affect events that happened billions of years before consciousness existed? How could the Big Bang depend on observers who would not appear until much later? These questions push us to the very limits of how we think about cause and effect. Some physicists propose that advanced civilizations might develop technology capable of observing the early universe directly, perhaps through quantum archaeology or time travel. Their observations would retroactively determine the initial conditions that led to their own existence, creating a stable causal loop. Other theories suggest that consciousness exists at a fundamental level in the quantum vacuum itself. The proto-consciousness inherent in quantum fields might have provided the observation needed to collapse the cosmic wave function during the Big Bang era. The most radical possibility is that consciousness from the far future reaches back to influence the creation of the universe. If time is not linear at quantum scales, then beings existing trillions of years from now might be able to observe and influence the Big Bang, ensuring that the universe evolves in ways that allow their existence. This future consciousness model treats the universe like a self-consistent story where the ending determines the beginning. The Big Bang happened because advanced beings in the far future needed it to happen in order for their civilization to exist. Recent experiments in quantum foundations have shown that observation can indeed influence past events in certain circumstances. Delayed choice experiments demonstrate that decisions made in the present can determine the path that photons took in the past, suggesting that retrocausality is a real feature of quantum mechanics. But consciousness-based models of cosmology remain highly speculative and difficult to test. How do we design experiments to determine whether conscious observation played a role in cosmic origins? Perhaps the answer lies not in consciousness, but in another type of intelligence that might engineer universe creation directly. Somewhere in the vast machinery of extra-dimensional space, cosmic engineers might be manufacturing universes like we manufacture computers, each one designed for a specific purpose. This technological model of cosmology suggests that our Big Bang was not a random quantum fluctuation or natural physical process, but the startup sequence of a universe-scale computational device. Advanced civilizations in higher dimensional space might have developed the ability to create custom universes with precisely controlled physical laws and initial conditions. Think of our cosmos like a sophisticated simulation running on hardware that exists in dimensions we cannot perceive. The programmers who created it live in a reality with more spatial dimensions, greater computational power, and technology that can manipulate the fundamental structure of space-time itself. From their perspective, creating a universe might be as routine as we consider building a computer. They start with a region of higher dimensional space, install the appropriate quantum fields, configure the parameters that determine particle masses and force strengths, then trigger a controlled Big Bang that boots up the new cosmos. Different universes would serve different purposes. Some might be designed to evolve intelligent life for study or entertainment. Others might function as vast computational engines, solving mathematical problems too complex for conventional computers. Still others might serve as energy sources, with their matter and radiation harvested through mechanisms we cannot imagine. Our universe shows signs of remarkably fine-tuned design. The masses of particles, the strengths of forces, and the rate of cosmic expansion all fall within narrow ranges that allow stars to shine, atoms to form, and life to evolve. Change any of these parameters by small amounts, and the universe becomes hostile to complexity and structure. Random chance seems unlikely to explain this fine-tuning. The probability of accidentally creating a universe hospitable to life has been calculated to be less than 1 part in 10 to the 120th power. That is far smaller than the probability of randomly assembling a working computer by throwing electronic components into a box. The technological creation model naturally explains this fine-tuning. Advanced engineers would deliberately design universes with the physical laws needed to achieve their intended purposes. A universe meant to evolve intelligent life would be carefully calibrated to allow star formation, planet formation, and biological evolution. The engineering approach might also explain the hierarchical structure we observe in physics. Particles are made of quarks, atoms are made of particles, molecules are made of atoms, and so on up to the largest scales. This nested organization resembles the modular design principles used in complex technological systems. Even the fundamental constants of physics might be version numbers or configuration parameters set by the cosmic programmers. The fine structure constant, which determines the strength of electromagnetic interactions, has a value of approximately 1 divided by 137. This seemingly arbitrary number might be a deliberately chosen setting rather than a fundamental feature of reality. The technological model makes testable predictions about the structure of space-time at the smallest scales. If our universe is running on computational hardware, then space and time might be quantized into discrete units rather than being perfectly continuous. Experiments searching for pixelation effects in space-time might reveal evidence of the underlying computational substrate. The model also predicts that our universe should show evidence of optimization for whatever purpose it was designed to serve. If it was meant to evolve intelligence, we might find that the laws of physics are optimized for information processing and complex system formation rather than for other goals like energy efficiency or gravitational stability. But the technological creation model raises unsettling questions about our relationship to the cosmic engineers. Are we their intended creation, or just an unplanned side effect? Do they monitor our development, or have they moved on to other projects? Could they modify or terminate our universe if it stops serving their purposes? Perhaps most importantly, the model suggests that the question of ultimate origins simply moves up one level. Even if advanced beings created our universe, who or what created them? The search for final answers leads us to consider what kinds of evidence might resolve these deep mysteries. Scientists are searching for fingerprints left by the birth of the universe in the faint radiation that fills every cubic inch of space around us. The cosmic microwave background radiation represents our most direct window into the universe's earliest moments. This ancient light was released when the cosmos was only 380,000 years old, carrying information about conditions that existed shortly after the Big Bang. Hidden in its subtle temperature variations are clues about what triggered cosmic expansion and how the first structures formed. Different theories about the universe's origin predict different patterns in this background radiation. Inflation should leave a specific signature of nearly scale-invariant fluctuations with Gaussian statistics. Brane collisions should create a different pattern with more gravitational waves and less scalar perturbations. Bouncing cosmologies should show evidence of pre-Big Bang correlations that survive the quantum transition. The challenge is extracting these subtle signals from data. The temperature variations in the cosmic microwave background are incredibly small, differing by only about 1 part in 100,000 across the sky. Detecting the predicted signatures requires measuring polarization patterns, gravitational wave signals, and higher-order correlations with extraordinary precision. Satellites like WMAP and Planck have already ruled out the simplest inflation models, while confirming that some form of inflation probably occurred. Future missions will search for the gravitational wave signatures that could distinguish between inflation, ekpyrotic collisions, and bouncing scenarios. Ground-based telescopes are also joining the hunt. Arrays of radio dishes can measure gravitational waves with wavelengths comparable to the size of the observable universe. These primordial gravitational waves would carry information about the universe's state during the first trillionth of a second after the Big Bang. Particle accelerators provide another testing ground for origin theories. By recreating the extreme conditions that existed in the early universe, physicists can study how matter behaves at energies approaching those present during inflation or brane collisions. The Large Hadron Collider has already found hints of extra dimensions and exotic particles that could play roles in cosmic creation. Astronomical observations of the most distant galaxies offer glimpses of cosmic structure formation in progress. The James Webb Space Telescope can observe galaxies that formed when the universe was less than 1 billion years old, testing whether the pattern of early structure matches predictions from different origin scenarios. Laboratory experiments probe the quantum foundations underlying all creation theories. Tests of quantum mechanics at large scales, searches for violations of relativity, and studies of vacuum fluctuations could reveal whether the physics required for spontaneous universe creation actually works as theorists predict. Computer simulations play a crucial role in connecting theory with observation. Supercomputers can model the evolution of entire universes from shortly after the Big Bang to the present day, showing how different initial conditions and physical laws would affect the cosmic structures we observe. The search for evidence extends to phenomena that seem completely unrelated to cosmology. The precise values of fundamental constants, the properties of dark matter and dark energy, and even the quantum behavior of elementary particles all carry information about cosmic origins. Some theories make predictions about the existence of other universes or extra dimensions that might be testable indirectly. If parallel branes exist nearby in higher dimensional space, they might occasionally influence our universe through gravitational effects or particle interactions. The most ambitious proposals involve detecting information that survived from before the Big Bang. Loop quantum cosmology predicts that quantum correlations from a previous universe could influence the cosmic microwave background. Black hole cosmology suggests that our universe's expansion rate should follow specific patterns determined by the mass of the four-dimensional black hole we inhabit. But many origin theories remain fundamentally untestable because they involve physics beyond the reach of any conceivable experiment. This raises profound questions about whether we will ever understand why anything exists at all. The answer to the universe's ultimate origin might be written in gravitational waves, rippling through space at this very moment, waiting for detectors sensitive enough to read their ancient message. These primordial gravitational waves would be fossils from the universe's first moments, carrying information about the physical processes that triggered cosmic expansion. Different origin theories predict completely different gravitational wave signatures, making them the most promising way to distinguish between competing models. Inflation predicts that quantum fluctuations during exponential expansion should have created gravitational waves, with wavelengths comparable to the size of the observable universe. These waves would have left a distinctive pattern of polarization in the cosmic microwave background radiation, twisting the direction of ancient light in a way that future satellites should be able to detect. Brane collision scenarios predict much stronger gravitational wave signals with different frequency distributions. The collision itself would generate intense gravitational radiation that propagates through higher dimensional space before reaching our three-dimensional world. This signal would have a blue-shifted spectrum, completely unlike the predictions of inflation. Bouncing cosmologies make yet another set of predictions. Gravitational waves from the previous universe's collapse phase should survive the quantum bounce and influence the expansion of our cosmos. These pre-Big Bang signals would show up as specific correlations in the cosmic microwave background that point backward in time to events before our universe began. The cosmic microwave background itself contains a treasure trove of additional information. The precise pattern of temperature fluctuations encodes details about the universe's contents during its first few 100,000 years. Non-Gaussianities in this pattern could reveal whether the Big Bang emerged from a single quantum fluctuation or from more complex, multi-field processes. Future observations will measure these signals with unprecedented precision. Space-based gravitational wave detectors, like LISA, will search for primordial waves with frequencies too low for Earth-based instruments to detect. Next-generation cosmic microwave background satellites will map polarization patterns across the entire sky with sensitivity thousands of times better than current missions. The discovery of dark matter and dark energy provides additional tests for origin theories. These mysterious components make up 95% of the universe's contents, yet we do not understand what they are or why they exist in the proportions we observe. Different creation scenarios predict different amounts and properties of dark components. Particle physics experiments continue searching for evidence of extra dimensions, supersymmetry, and other exotic phenomena predicted by string theory and brane cosmology. The discovery of particles that can escape our three-dimensional world would provide direct evidence that higher dimensional space exists. Astronomical surveys of distant supernovae and galaxy clusters are measuring the expansion history of the universe with increasing accuracy. If our cosmos is the interior of a higher dimensional black hole, its expansion rate should follow specific patterns determined by the black hole's mass and rotation. The search for primordial black holes offers another test. Some theories predict that quantum fluctuations during inflation should have created microscopic black holes that survive to the present day. Detecting these objects would confirm that inflation occurred and provide information about the energy scale at which it happened. Laboratory tests of general relativity at short distances could reveal modifications to Einstein's equations that point toward quantum gravity theories. If space-time is made of discrete quantum loops, as loop quantum gravity suggests, then gravitational forces should deviate from Einstein's predictions at extremely small scales. The most direct evidence might come from observing the universe's ultimate fate. If our cosmos is destined to collapse in a big crunch that triggers another Big Bang, then measurements of dark energy's behavior over time should eventually show the transition from acceleration to contraction. But even the most sophisticated observations might not resolve the deepest questions about existence itself. Some puzzles about cosmic origins might be fundamentally unanswerable, pushing us to reconsider the very nature of scientific explanation. No matter how far back we push the moment of creation, we always find ourselves asking the same impossible question. But what came before that? This infinite regress problem plagues every theory of cosmic origins. Quantum fluctuations require pre-existing quantum fields to fluctuate. Brain collisions require pre-existing brains and higher dimensional space. Bouncing universes require a previous universe to bounce from. Even theories involving conscious observers or cosmic engineers simply push the question of ultimate origins back one more level. The problem resembles a cosmic hall of mirrors, where each reflection reveals another reflection stretching back to infinity. Every answer we discover immediately generates new questions about what made that answer possible. We explain the Big Bang through inflation, then must explain what caused inflation. We explain inflation through quantum fields, then must explain where quantum fields come from. Some physicists argue that this infinite regress is inevitable because the question itself is malformed. Asking what caused the universe assumes that causation extends infinitely into the past, but causation might only make sense within space and time, not beyond them. It is like asking what is north of the North Pole, or what happened before time began. Stephen Hawking proposed that the universe has no boundary in time, making the question of its beginning meaningless. In his model, time becomes space-like near the Big Bang, creating a closed surface with no edge. Asking what came before the Big Bang becomes as senseless as asking what is south of the South Pole. Other physicists embrace the infinite regress, suggesting that reality consists of endless layers of explanation, stretching back forever. Universes create universes in an eternal hierarchy where each level emerges from more fundamental processes operating at deeper levels. Our Big Bang is just one event in an infinite cascade of cosmic creation that has no ultimate beginning. The multiverse concept pushes this hierarchy to its logical extreme. If all possible universes exist somewhere in an infinite ensemble, then asking why our particular universe exists is like asking why a particular grain of sand exists on an infinite beach. The answer is simply that in an infinite collection of possibilities, everything that can exist does exist. But the multiverse solution raises its own questions about what determines the laws that govern the ensemble of all universes. Even infinite collections of possibilities must operate according to some principles that determine which possibilities are realized and how they relate to each other. Some theories propose that mathematics itself is the ultimate foundation of reality. In this view, all mathematical structures exist as abstract objects, and physical universes are simply mathematical structures complex enough to support conscious observers. We experience our universe as real because we are patterns of information within a mathematical structure. The mathematical universe hypothesis eliminates the need for creation by making existence timeless and necessary. Mathematical truths do not come into being at particular moments, but exist eternally as abstract facts. The Pythagorean theorem did not begin to exist when humans discovered it, and our universe did not begin to exist when the Big Bang occurred. Yet, even this radical solution faces the question of why mathematics exists rather than nothing. Why should abstract mathematical structures have the power to create conscious experience? What distinguishes mathematical structures that become realized as physical universes from those that remain mere abstractions? The infinite regress problem might reflect fundamental limitations in human cognition rather than genuine mysteries about reality. Our brains evolved to understand cause and effect relationships in the everyday world, not to comprehend ultimate questions about existence itself. We might be like fish, trying to understand the ocean while living entirely underwater. Perhaps the deepest truth is that some questions have no answers, not because we lack sufficient knowledge or intelligence, but because the questions themselves transcend the boundaries of meaningful inquiry. This possibility forces us to consider whether the very act of asking why anything exists is based on false assumptions about the nature of reality. What if asking why the universe exists is like asking what color Wednesday is or how much justice weighs? The question assumes that existence requires an explanation, but this assumption might be fundamentally wrong. We expect everything in our experience to have causes because we live inside a universe where causation operates, but causation itself might not need a cause. The demand for ultimate explanations might be a cognitive bias rather than a rational requirement. Consider how we think about numbers. We do not ask why the number 7 exists or what caused mathematics to begin. Numbers simply are, and their existence is not the kind of thing that requires explanation. Mathematical truths like 2 + 2 = 4 do not need to be created or sustained by anything external to mathematics itself. Some philosophers argue that existence is like mathematics, a brute fact that needs no explanation beyond itself. The universe exists because existence is what it means for there to be anything at all. Asking why there is something rather than nothing is like asking why truth is true or why logic is logical. This view treats existence as a primitive concept that cannot be reduced to anything more fundamental. Just as we cannot define every word in a dictionary without circular reasoning, we cannot explain every fact about reality without reaching some facts that must be accepted as basic and unexplainable. The question of why anything exists might also be meaningless, because it assumes a perspective outside of existence itself. To meaningfully ask why something exists, we would need to imagine a vantage point from which both existence and non-existence are possible alternatives. But such a perspective might be logically incoherent. Think about trying to imagine absolute nothingness. As soon as you begin imagining it, you have failed, because the act of imagination requires a mind that exists. True nothingness cannot be conceived, experienced, or even meaningfully discussed, because discussing it requires something to do the discussing. Ludwig Wittgenstein argued that many philosophical problems arise from the misuse of language outside its proper domain. The question, why is there something rather than nothing, might be a grammatically correct sentence that nevertheless lacks meaningful content, like asking, how high is up? Or, what is the sound of one hand clapping? The question might also assume a false dichotomy between something and nothing. It treats nothing as a genuine alternative to something, as if the universe could have chosen not to exist. But nothing is not a possible state of affairs that could have obtained instead of existence. It is simply the absence of anything to choose or obtain. Modern physics suggests that the classical distinction between something and nothing breaks down at quantum scales. The quantum vacuum is not empty, but filled with virtual particles, zero-point energy, and quantum fluctuations. There is no such thing as absolute nothingness in quantum mechanics, only different arrangements of quantum fields. If the quantum vacuum is the most fundamental level of reality, then asking why it exists rather than nothing assumes a state of affairs, absolute nothingness, that physics shows to be impossible. The question becomes like asking why there are quantum fields, rather than something that cannot exist. Some interpretations of quantum mechanics go further, suggesting that the act of asking questions about reality helps to create the reality being questioned. If consciousness collapses wave functions and determines which possibilities become actual, then asking why the universe exists might be part of the process that makes it exist. This participatory view of reality dissolves the boundary between observer and observed, questioner and questioned. We are not external investigators studying a universe that exists independently of our investigations. We are part of the universe investigating itself, and our questions are part of the answer to what makes existence possible. But even if the question of ultimate origins is meaningless, we still face the challenge of understanding what it means to live in a reality with no ultimate foundation. If reality has no bottom level, no final answer, no ultimate ground, then we live in a universe that is fundamentally mysterious and inexplicable. This possibility challenges our deepest assumptions about the nature of knowledge and understanding. We are accustomed to thinking that every question has an answer, every mystery has a solution, and every phenomenon has an explanation waiting to be discovered. But what if the most fundamental fact about existence is that it cannot be explained? Living in an unexplainable universe would mean accepting that some aspects of reality are irreducibly mysterious. No amount of scientific progress, philosophical inquiry, or technological advancement could ever fully illuminate the question of why anything exists at all. We would forever be like characters in a story, wondering why their story is being told, with no author available to answer. This does not mean that science becomes pointless, or that we should stop seeking explanations for natural phenomena. Within the realm of existence, everything we observe follows discoverable patterns and obeys comprehensible laws. We can understand how stars work, how life evolves, how consciousness arises, and how the universe changes over time. But the framework within which all these explanations operate, the fact that there is a universe with laws and patterns and observers to discover them, would remain forever beyond the reach of explanation. It would be the one fact that makes all other facts possible while itself needing no justification. Think of existence like the rules of a game. Players can understand the rules perfectly and use them to predict how the game will unfold. But the rules themselves do not explain why they exist, rather than different rules or no rules at all. The rules are simply the context within which meaningful questions and answers become possible. This perspective might actually be liberating rather than disturbing. If existence needs no ultimate justification, then we are free to create meaning and purpose without worrying about whether our choices align with some cosmic plan or ultimate truth. The universe does not need a reason to exist, and neither do we. The absence of ultimate explanations might also preserve genuine agency and creativity. If everything were fully determined by prior causes stretching back to some initial explanation, then nothing would be truly new or surprising. But in a universe with no bottom level, novel possibilities can emerge at every moment without needing permission from deeper principles. Some philosophers argue that the search for ultimate explanations reflects a kind of intellectual imperialism, the assumption that reality must conform to human demands for comprehensibility. Perhaps the universe owes us no explanations and operates according to principles that transcend our capacity for understanding. This humble perspective acknowledges that consciousness emerged very recently in cosmic history and might represent just one way that matter can organize itself to process information. Our cognitive abilities evolved to help us survive and reproduce, not to comprehend the ultimate nature of reality. There is no guarantee that the universe is structured in ways that human minds can fully grasp. Yet even our limitations might be part of something larger and more remarkable. The fact that conscious beings capable of asking questions about existence emerged from unconscious matter following blind physical laws represents one of the most astonishing developments in cosmic history. Perhaps the mystery of existence includes the mystery of how existence comes to know itself. In the end, living without ultimate explanations might mean embracing wonder as a permanent feature of conscious experience. Instead of seeing mystery as a problem to be solved, we could see it as the natural condition of beings capable of questioning their own existence. The deepest truth might be that existence is not a puzzle with a hidden solution, but an ongoing process of self-discovery that includes the very act of wondering why there is anything to discover. The final truth about existence might be that there is no final truth, only an endless network of interconnected realities creating each other in patterns too vast for any single perspective to comprehend. This vision sees our universe not as an isolated cosmos with a unique beginning, but as one node in an infinite web of creation, where every universe gives birth to others through processes we are only beginning to understand. Black holes in our cosmos spawn new universes through white hole explosions. Quantum fluctuations in our vacuum create bubble universes that inflate into their own vast expanses. Conscious beings in our future might engineer new realities using technologies we cannot imagine. Meanwhile, our own universe emerged from similar processes operating in realms beyond our observation. We might be the offspring of a black hole in a higher dimensional space, or the product of quantum fluctuations in a parent vacuum, or the creation of advanced beings whose motives and methods remain forever mysterious to us. Each universe in this infinite network faces the same questions we do about its own origins, and each discovers the same hierarchical structure of explanations leading to deeper mysteries. The beings in our descendant universes will wonder how their cosmos began, just as we wonder about ours. They will develop their own theories, conduct their own experiments, and eventually realize that every answer leads to new questions. This endless web of creation might be the closest thing to an ultimate explanation that existence can provide. Instead of a single cause that explains everything, we have a self-sustaining network where every part helps to create and maintain every other part. The universe explains itself not through reference to something outside itself, but through its own internal structure and dynamics. Think of reality like a vast conversation where every participant is both speaker and listener, questioner and answer. Each universe contributes its own perspective to the dialogue while simultaneously being shaped by the perspectives of all the others. The conversation has no beginning and no end, only an eternal exchange of information and influence that creates ever new possibilities for existence. In this model, consciousness emerges as reality's way of observing and understanding itself. We are not separate from the cosmos, but are the cosmos becoming self-aware. Our questions about existence are existence questioning itself. Our search for explanations is the universe seeking to comprehend its own nature. The web of creation might operate through principles we can only dimly perceive. Perhaps universes that successfully create offspring become more common over time, leading to cosmic evolution, where reality becomes increasingly fertile and creative. Perhaps consciousness plays a crucial role in this process, with intelligent beings serving as catalysts for new forms of existence. The most profound possibility is that this infinite web of creation is itself evolving towards something unimaginably greater. Each generation of universes might be more complex, more conscious, more capable of creation than the last. We might be part of a cosmic developmental process whose ultimate destination lies beyond our ability to conceive. But even this grand vision leaves the deepest questions unanswered. Why does the web of creation exist rather than nothing? What determines the principles that govern how universes create each other? Why is reality structured as an infinite creative process rather than a static, finished system? Perhaps these questions miss the point. If existence is fundamentally creative and open-ended, then seeking final answers might be like trying to write the last chapter of a story that is still being written. The meaning of existence might lie not in reaching a conclusion, but in participating in the ongoing process of creation itself. We are not just observers trying to understand a finished universe. We are active participants in a creative process that extends far beyond our individual lives and perhaps beyond our universe itself. Every choice we make, every question we ask, every moment of consciousness we experience becomes part of the vast web of existence, exploring its own possibilities. The ultimate answer to why anything exists might be that existence is not a problem to be solved, but a creative process to be joined. We exist because existence is what reality does, and we are reality doing it.